In this example, we're asked to look at a system which is made up of this L-shaped bracket ABC, which is pinned to ground at B, and two rods, 1 and 2, connected to that bracket at locations A and C. What we know is that we're going to be increasing the temperature, or I should say changing the temperature of segment 1 by an amount of delta T that will end up being a minus 50 degrees F. And we're going to keep the temperature 2 the same. As a result of that, what are the axial stresses induced in rods 1 and 2? And secondly, what's the transverse shear force and the bending moment, the cross-section there at the midpoint between A and B? As always, we're going to start out with free body diagrams. What I'm going to do is first show the rods there of 1 and 2. As always, my approach here is going to be writing the axial load, showing the member as being in tension. I don't know whether it's going to be in tension or in compression, but I'll let math take care of itself. With that, though, by Newton's third law, F1 is going to be acting downward there at A. If I look at member 2, rod 2, if I show those forces on the ends as representing those from being in tension, then the force on C is going to be to the right. I'm going to use a coordinate axis here of x positive to the right and y as being positive up. Our equilibrium equation, the one I'm going to write down, is a moment equation about point B. So for the L-shaped bracket, summation of moments about B, F1, that has a moment arm of 2a. By the sign conventions I chose, that's going to be a plus sign. F2 has a moment arm of a, and it also is plus. For equilibrium, that is a 0. So what I get here is that F2 is going to be equal to minus 2F1. That's my first equation. Unfortunately, that's all we have from equilibrium. So with one equation and two unknowns, we know, and not too surprised, but we know that this problem is indeterminate, which means that we need to write down our elongation and compatibility equations before we try to solve for those loads. We need to pick up our additional equation or equations to get there. So our elongation equation for segment 1, that's going to be F1L1 divided by E1A1. That's due to the axial load. Due to the change in temperature of delta T, that's going to be alpha delta TL1. And so this becomes F1L, that's the length of 1, divided by EA plus alpha delta TL. So this is equation 2. The elongation equation for segment 2 will just be that due to the axial load. We know there's no temperature change, so there's no thermal expansion contraction term there. So this becomes F2. It has a length of L, and of course EA there on the bottom. So that's my third equation. Please note that with the way I've written things down, I need to put delta T in here as being a minus 50 degrees F. That minus sign needs to be included because it says that the temperature of 1 is decreased. What is our compatibility? What is the relationships that exist between E1 and E2? Let's go back up to here. To the right of my FBD, I've shown the rod, this L-shaped bar with a rotation angle there of theta, positive rotation. And for that positive rotation, we have movements here of A and C. This is going to be due to the elongation of 2, this one to the elongation of 1. So from that picture, we can write down our compatibility equations. as being that theta for small angles of rotation here is going to be the inverse sine of E1 over 2a, and for small angles, which is what we're supposed to consider here, the angle and sine of the angle are one and the same. Same angle there of rotation for that bar, but looking at its relationship back to E2, that's going to be E2 divided by A. Again, for small angles, E2 over A, like that. So what we have is that E1 divided by 2A is equal to E2 divided by A. So E2 is a plus 1/2 E1. So that is my equation 4. So now we have 4 equations. We have 4 unknowns we can now solve. Again, because it's indeterminate, we need to solve these in a simultaneous way rather than a sequential way that we would be able to use if it were not indeterminate. I'm going to grab equations 2 and 3 and 4. I want to end up with F2 over EA times L is equal to 1/2 F1L over EA plus alpha delta TL. So this is my compatibility equation with my elongation equations put in there. So the relationship that I was looking for here that relates F1 to F2 is right here. F2 is equal to F1 times 1/2 plus 1/2 EA alpha delta T. Again, we were looking for that additional equation. We've got it. So now I take the original equation, equilibrium equation 1, combine it with my equation 5, F2 being equal to minus 2F1. That was from equilibrium. So I have F1 over 2 plus 1/2 EA alpha delta T. That's equal to minus 2F1. One equation and one unknown. And so from this I get the F1 is equal to minus 1/5 EA thermal expansion coefficient of alpha times the temperature change there on delta T. So this is the relationship that we have. Please keep in mind here that the delta T that we're going to have, let me just confirm by looking back on this, it says that the temperature is going to be decreased. So since delta T is negative, it means that F1 itself, a negative times a negative is a plus. So this says that segment 1 is in tension. Solving for F2. F2 will end up being 2/5 EA delta T. And again, since delta T is negative, it says in this case F2 itself is negative, so F2 is in compression. As a result of the thermal contraction there on 1, that's what that's going to do is compress 2, and that makes sense. We go back to our goal here. Our goal here was to find sigma 1. That's equal to F1 over A. So that ends up being minus 1/5 E alpha delta T. the stress in segment 2, which is F2 over A, so that ends up being 2/5 E alpha delta T. So these are the stresses that are induced in 1 and 2 as a result of that thermal contraction there at 1. We're asked now to do some internal force analysis of that L-shaped bar. So what I'm going to do here is make a cut. This is the L-shaped bracket like this. We're asked to find out what the bending moment and the shear stress is at the midpoint there between A and B. So if we just draw a free body diagram of that piece, I've got F1 like this. I'm going to draw a V down like this, and bending moment M. And please note that we're doing this at the midpoint there between A and B, called point D. So if I do a summation of moments of that segment there, about the end D, I get F1 moment arm of A. The bending moment M, that's a 0, so the bending moment at D is going to be equal to minus F1A. So that ends up being 1/5 EA alpha delta T times the dimension there of A. Summing forces in Y. The Y direction, I've got minus F1 minus the shear force V, by the way that I drew it there in my picture. So from this, I see that the shear force is equal to minus F1. So that is ending up being a 1/5 EA alpha delta T as that. So this is the bending moment, and this is the shear force. So just going back over what we did, drew the FBD of the L-shaped bracket. And what I did, which is going to be consistent with what we're going to do here all semester, is I'm going to show that member, both members 1 and 2, as being in tension. I don't know in advance which one is which, or at least I don't care what it is when I draw the FBD. I'm just going to show them both in tension and carry that all the way through. So that dictates the direction for F1 there in the bar and F2. Equilibrium, we get one equation. We need to use our elongation equations. This is where the sign conventions are important. By drawing it that way, I don't have to worry about signs here. I just write down my equations. And finally, I need to then say what that relationship is going to be between E1 and E2. Again, abiding by the sign conventions that I have, you can see here that the relationship between E1 and E2, that's going to be a plus sign just based on the kinematics. That gave me all the equations that I need. I solved them in a simultaneous way in order to get the loads carried by these segments, and then from that I can find stress. I can also calculate the shear force and bending moment there through the cut through that L-shaped bar.